This video is going to cover the different applications of quadratics. We are really going to focus on projectile motion, but there are several different applications different ways that you can use quadratics and applications that they're used in. So if you are the kind of person who likes to ask, when are we ever going to use this? This is your day, because we are going to answer that question, when are you ever going to use this? One of the most common applications of quadratics is in something called projectile motion. Projectile motion means that you launch something straight up or at an angle or whatever, but you launch something and it comes back down. And when that happens, if you launch it at an angle, it creates a parabola, and you can see that parabolic motion. If you launch it straight up, you can't see the parabolic motion, but when we graph height over time, it does follow a parabolic path in that regard, and so we'll talk about that a little bit. So here we talked about what a projectile is: an object thrown, shot, or dropped, usually straight up or straight down. These problems use a function that represents the object's height, which depends on the force of gravity pulling it back down, and the initial velocity at which it was thrown or dropped, and the initial height. So this equation is actually a physics equation. It's modified a little bit for a couple of things, but it is essentially a physics equation. The negative 16 here actually comes from gravity. The force of gravity is negative 32 feet per second squared. So when we have a negative 16, it's because in the original equation there's a 1/2. And so the 1/2 is what gives us that negative 16. So this equation is an equation that we use to find how high something goes. The T stands for time and the H stands for height. So that's why on the graph I have over here in the margin, the time is on the x-axis and the height is on the y-axis. If you haven't drawn that yet, go ahead and take a second to draw that in the margin. But basically, this equation is what we're going to use for all of these problems, and we're just going to be plugging in different parts of it, but you can see that it is a quadratic. It's a t squared term, so that is a quadratic, and so everything we've learned about quadratics will be used here. Let's go ahead and look at the first example. An object is launched directly upward at 64 feet per second from a platform 80 feet high. Write the function for the height of this object at any given time with t in seconds. We are basically going to use this equation every time. And as you look at this equation and you look at the diagram I have set up over here, I think you can see that the x-axis is time and our y-axis is the height. So anytime it asks about time, it's really asking about the x, and anytime it asks about the height, it's really asking about the y. So we are going to start this equation. We're always going to start it with a negative 16t squared. That's how it's always going to start. Now, the initial velocity here is 64 feet per second, and that's followed by a t, and then our initial height is 80 feet high. So that's the equation that we're going to use for this problem. Question A, when will the object reach its maximum height? What is this really asking? Okay, when this object gets thrown up and then it comes back down, the maximum height is really the vertex, isn't it? So this is really asking, how high is the vertex? Or actually, this one is asking, when will it reach the maximum height? So we're asking about time in this case, because we want to know when. So we're looking for the vertex, but we are really looking for the x portion of the vertex, because it's time. And we have learned in our quadratics that the way you find the vertex is x equals negative b over 2a. That's going to give us the x value of the vertex. So we look up here and we plug in a negative b over 2a. And so when we plug all of that in, we get 2. Well, 2 what? The question was when, and x is time, so it's 2 seconds. The object is going to be thrown up in the air, and it's going to be up in the air for 2 seconds before it reaches its max height. The next question is, what will that maximum height be? So again, we look at our diagram, and now we're talking about how high is it going to go. So now we're talking about the vertex, but we're talking about the y part of the vertex. And so what we did to find the y part of the vertex is we can use h of t, because that's the height. We want to know how high is it after 2 seconds. And so we will plug that 2 into our equation and work it out. So we plug in our numbers and we work it out and we get 144. 144 what? Well, we're looking for height, and we're talking about, the whole thing we've been doing is measured in feet. So we're going to say it's 144 feet. That is the max height. Okay, so that's the maximum. That is the vertex. The highest it gets, and we can come over here to our diagram and maybe fill in some information. The highest it gets is 144, and it reaches that height of 144 after 2 seconds. Obviously, there are infinite number of points along the way, but that is our vertex, and that's an important piece. We need that vertex. But the next question, question C, is asking us, how long is it going to take to reach 100 feet? So it starts at 80. The highest it gets is 144. We want to know, and I'm just going to estimate here where this would be, we want to know how long is it going to take to get to 100. Okay, think about our variables. This is on the y-axis, so we're talking about h is 100. So we're talking about, I'm going to take this original equation that we came up with, and I'm going to put in 100 in for the height. And what we're looking for is the time, because it says how long, that's t, that's what we're looking for. So I'm going to put 100 in for the height. So we need to solve for t. We've learned a couple different ways to solve for t. Sometimes we factor, sometimes we use the quadratic formula, sometimes we just solve. In this case, we can't just solve because that 64t is there. But so we either need to factor it or find the quadratic formula. But either way, we need to move that 100. So we need to subtract that over. So I'm going to go ahead and do that first. And so now that I have it in a standard form, a couple things I see. I could divide out a 2 and see if that helps my case. But I'm looking at this and I'm thinking that's going to be really hard to factor. Even if I factor out a 2, or I could factor out a 4, maybe if I factor out a 4 I could factor it, but I'm just thinking that quadratic formula might be a lot easier. So I'm going to go ahead and set this up for the quadratic formula. Take a minute to do that. You could pause the video here, set up your quadratic formula, plug in your numbers, and see what you get. One thing along the way is when I plugged it in, I left my negatives here as they were in the original equation. If you wanted to divide it all by -1, so you had a positive 16, a negative 64, and a positive 20, you could do that, but I'm going to go ahead and leave my negatives and positives the way they are in the original equation. It doesn't make any difference. You can do it either way. So now I'm going to go ahead and calculate this, and I should be able to put this just into my calculator. I'm going to go ahead and calculate it and see what I come out with. Since it is a word problem, we really want decimals. It wouldn't make sense to tell anyone radical 2 seconds or something like that. So I'm going to go ahead and make it into decimals when I do this. Okay, I ran out of space in my part C, so I came over here to the margin. And after you calculated this and simplified some of it, you should have gotten -64 plus 53.06 over -32, and 64 minus 53.06 over -32. And some people, I think, are still unclear on how to do that, but what you really need to do is just add -64 plus 53.06, and that comes out to be 10.94. And then you also subtract -64 minus 53.06, and that comes out to be -117.06. And in both of those cases, we're going to divide by -32. So we divide that, and when we get that, we get a positive 3.66 seconds and a positive 0.34 seconds. Sometimes when you do this, you'll get a positive answer and a negative answer, and we'll talk about that when it happens because there will be an example like that. But on this one, we actually have 2 different answers. Let's look at our graph and figure out why do we have 2 answers. The first one is really small, 0.34, because look at the graph. We're talking about right here. And that's just going to take barely any time, 0.34 of a second, to get to that height. But then it goes all the way up and it comes all the way back down, and on its way down we have this one over here, and that is 3.66 seconds later. And so the answers to part C, there are actually 2 answers. And your 2 answers are 3.66 seconds and 0.34 seconds. And again, since it is a word problem, it just doesn't make sense to give radical answers, so we will go ahead and give decimal answers on that. Let's take a look at example number 2. A baseball is thrown straight up in the air with an initial velocity of 29 feet per second from a point exactly 6 feet off the ground. Write the function for the height of this object at any time. Well, first of all, I did come over here and I drew a diagram again, starting at 6 feet high, and we're going to have to figure out some information on the time and the max height and all that. But also, I need to fill in the equation, so I'm going to go up to the top and look at that equation again. This is the equation that we need to use, so we're going to follow this equation. So I'm going to start with a negative 16t squared, that's what I always start with, plus, next thing is original velocity. The initial velocity is 29 feet per second, and then where it starts from 6 feet off the ground. Notice that's our y-intercept, right? It starts from 6 feet off the ground, that's our y-intercept. Okay, part A, when will this object return and hit the ground? What is this really asking? So look at this problem. When will it hit the ground? First of all, it's a when, so we're talking about time. And secondly, we're talking about when it hits the ground, so we're talking about right here. On the graph, what is that point called? That's our x-intercept. So we're looking for our x-intercept. So we're looking for how to figure the x-intercept from this equation. Also, at this point, what is the height at this point? When it hits the ground, how high is it? Well, it's 0 feet high. So we can take this equation and plug in a 0 for our height. And when we do that, now we can solve this as a quadratic. Once again, I could think about how to factor this, and I probably could factor it, but it just seems like quadratic formula might be a little bit easier given the fact that the numbers are just not really very easy to deal with. So I'm going to go ahead and use the quadratic formula. Take a second right now, pause the video, and set up for the quadratic formula. Okay, this time when I did the quadratic formula, it turns out my discriminant was a perfect square, and that makes it a lot easier. So I probably could have factored this, but that's okay. I did a quadratic formula. I'm going to get an answer here. The square root there is 35. And so really what I have is a negative 29 plus 35, which is 6, divided by negative 32, and a negative 29 minus 35, which is negative 64, divided by negative 32. And so if I divide those, this one comes out to be a negative 0.1875. This one comes out to be a positive 2.0. And again, they were when, so this is seconds and this is seconds. Let's look at our graph. Where are those going to be on our graph? Well, we had highlighted this point saying that was the point we were looking for, and in fact that is the point, the 2.0 seconds right there. And so what you might ask is, well then what is this negative decimal number, this negative 0.1875? Well, come back to the graph and look, if I continued this parabola on, it's going to come down here somewhere. And that's what this number is. This number is, where did it hit over here, which is negative 0.1875. Of course, we can't have negative time, so that doesn't make any sense. But that's just what that number is, so you know when you come up with it, you know where it's coming from. It's coming from this intercept over here. So let's go ahead and cross that one out. That does not work, but this one is our answer. It takes 2 seconds for it to go up, come down, and hit the ground. The next question asks, how high will it be after 0.5 seconds? Remember, seconds is time, right? So if we go to our equation, the question is asking how high will it be? Well, we can find the height by plugging in. The height after 0.5 seconds is, and then plug in our 0.5. And so we just plug in our 0.5 all the way, and we simplify this. And so I just plug this into my calculator, and when I plug it in, I get 16.5 feet, and that just says that after 0.5 seconds, it's going to be 16.5 feet high. We might just look at the graph and see if that makes sense, because on the graph, this was 2. All right, I have a question for you. Is the vertex going to be exactly at 1? Not really, because it's kind of scooted over. See what I mean? It's not at 0 here, so it's kind of scooted over. So 1 might be over a little bit from there, maybe more like that. But this question was asking about 0.5, which is right about here, 0.5. It started at 6 feet high. We never did find the vertex, so we don't really know how high it is, but we're saying at 0.5 seconds, it's going to be right about here at 16.5 feet. That's what that's saying to us. On the second page, we have another example. This example does not follow the same equation. It is the same equation, but it's a different form. Remember, the ones we were doing on the last page, they were all standard form, right? But we've learned vertex form, we've learned factored form, and we've learned standard form. So maybe we can do one of those other forms, vertex form or factored form, even though we have all this information that right now looks like a bunch of crazy information. But let's take a look at what it is. So we have a graph over here. And we're going to go ahead and plot some points. It says that your average launch reaches a maximum height of 286.7656 feet. It's very accurate measurements. And it's in the air for an average of 8.45 seconds. That is our vertex, right? Remember, time is going to be down here on the x-axis. Height is going to be on the y-axis. So the max height is 286.765, and that the average time is 8.45 seconds. Well, wait a second. 8.45 seconds, that's going to be over here. Well, what's half of 8.45? Because whatever is half of 8.45 is going to be where the vertex is. And half of 8.45 is 4.225. And then the height at that point is 286.7656. Write an equation to model this situation. Oh, we also have another one. After 1.89 seconds, the potato is 200 feet off the ground. Let's think about where that is on our graph. 1.89 seconds, maybe about here. And they're saying when that happens, that it's about 200 feet over here. So we have a point there that we can use. I'm going to write it up here. That point is 1.89 and 200 feet off the ground. So this is going to be a point that we could use. All right, look at what we have. We have a vertex. We have a second random point. We can use vertex form. The only thing we need for this vertex form is we need to know what is A. Well, just like on the other side of the page, every time the A was negative 16, well, guess what? This is going to be negative 16 also. So we can use that information. Now, we could derive that. We could do an example like we were doing the first time we did this stuff a couple of days ago and find that 16, that A, but we don't need to because we know gravity, that's what we're going to use. So let's use vertex form. I'm going to remind you what is vertex form. This is vertex form. So we're going to plug in. We're going to say y equals, the A is negative 16. X is just x. And then h and k are, those create our vertex. So h is the x value, that's 4.225. And if you're not sure which one goes with what, remember that this is the x value. If this is the x value, it goes with the x. And then the y value goes outside. It tells us how high it goes. So this is the equation that we're going to use. Now the question says, after how many seconds will the potato be 100 feet off the ground? Well, a couple things. Do you see how we had 1.89 with a 200? And so maybe it's just half of that. But actually it's not. That's not the way gravity works. Gravity is acceleration. And we have a parabola, so it's following a parabolic path. It's not going linear. If it was linear, we could just divide this in half and we'd have our answer. But it's not linear. It's parabolic. So we have to plug in some numbers. So after how many seconds, we're looking for time. Will the potato be 100 feet off the ground? 100 feet is our height. So you see height on the y-axis. So I need to plug in 100 over here. And so I'm going to plug in that 100 over there. And now I'm going to work this out. And we've worked out problems like this in the past couple of days recently. So I need to subtract that 286.7656 from both sides. So I have a negative 186 0.7656. And then I have that negative 186, but I need to divide it by 16. So I'm going to divide by 16 on both sides. And when I do that, I get a positive 11.67285. So I'm not rounding it yet. I'm going to round at the very end. Next step, as you look at this, we're going to need to take the square root of both sides. So let's go ahead and do that. Okay, I went ahead and finished out the problem. So I divided by 16, and then I took the square root. And when you take the square root in the middle of an equation, you have to give your plus and minus. So I had plus and minus 3.4166. Then I needed to add that 4.225 to both sides. And so remember, what that means is you're doing two things. You're taking a positive 3.4166 plus 4.225, and you're taking a negative 3.416 plus 4.225. And so your two answers are 7.642 seconds and 0.808 seconds. And once again, if you look up at the graph, this time we're talking about reaching 100 feet. And so we're saying it the first time it hits that is at 0.808 seconds. And then the second time it hits it is over here at 7.642 seconds. Okay, so that answers the question of after how many seconds will it be 100 feet off the ground? Going up and coming down. Next question is how high will it be after 1 second? So let's go back to that original equation and plug in 1 second for the t. Well, the t is the x. So I'm trying to find the height. The height is the y. So I'm going to say y equals, and I'm going to plug in for the x. Okay, so when I plug into this formula and I plug in a 1 for 1 second, I work this out. And I'm showing a lot of steps here, but some of you just put this straight into the calculator, and that's fine too. Do at least show me your first step, but then if all of this is just calculator work, you don't have to show all that if you don't want to. I just like to do it because it just shows you what I'm doing. So when I do that and I add all that together, I get 120.35 feet. So this problem, which the other day when we looked at it on the notes looked like it was impossible, it actually isn't impossible. Now that we've learned that the gravity is negative 32 and we're supposed to take half of that, so it's negative 16. So that's our A. And we've learned about the vertex form. This problem actually becomes pretty easy. It's not too hard at all. And once again, we didn't derive that negative 16. We could have worked this out with an A and plugged it all in and worked it out, and it would have come out to negative 16. I'm going to assume that you just want to take my word for that and you don't want to see that worked out. But we could work it out if we needed to. All right, at the bottom of this page is going to be the work that you're going to do in class tomorrow. So don't worry about doing it now. We will have class time tomorrow to do it. Tomorrow we can go over questions if you've got questions about the examples that we've done as well.